Today we're going to start section 1.4, and we're going to introduce the matrix equation AX equals B, where A is a matrix, X is a vector, and B is also a vector. Okay. We can represent A in notation with the following column vectors. For example, if A is 1, 3, 2, 2, 1, 5, 0, 0, 1, let's say, then this would be A1 would be the column vector 1, 3, 2. A2 would be this column vector 2, 1, 5. And A3 would be the column vector 0, 0, 1. Okay, so this is just notation. It's how we represent a matrix using column vectors. Okay. And X is a column vector x1, x2, dot, 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 xn. Okay. And so we can see here that a matrix times a vector, this matrix times this vector, is simply A1, A2, AN, the column vectors, multiplied by x1, x2, dot, 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 xn. Okay, which by definition is x1, A1 plus x2, A2 plus dot, dot, dot plus So, for example, we can see if we had, well, yeah, you can use numbers here if you'd like. So if we had A equals 1, 0, 2, negative 5, negative 1, 3, times 4, 3, 7. Now notice something here. The number of columns here is the same as the number of rows. Okay? And this needs to be, this is a condition for this multiplication here. All right. So we will have, this is 4 times 1, 0, plus 3 times 2, negative 5, plus 7 times negative 1, 3, which is 4, 0, plus 6, negative 15, plus negative 7, 21. And we can add these three by just adding these three here. So we will get negative 1 plus 4, which is 3, 6. And this is the answer, right? You'll see in a second why, well, you should see here why this is important. And this equals B, let's say, right? Why is this important? Well, we learned in the last section this vector equation can represent a system of linear equations. now we're just giving you a different way with a matrix equation. And we're showing you that this particular matrix equation is a different way of representing this vector equation, which is a different way of representing a system of linear equations. Okay? So let's present the following theorem. A M by N matrix with columns A1, AN, from A1 to AN, and let B be a vector in M-dimensional space. Then the matrix equation AX equals B has the same solution set as the vector equation x1 a1 plus dot 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 plus equals b, which has the same solution set as the system of linear equations with augmented matrix A1 to AN and B. Okay, so what does that mean here? That means if I give you a matrix, let's say 1, 3, 3, 2, 1, 2, 2, 2, 1, and I do not give you some vector x, but I tell you that this matrix times x will give you some b, another vector, okay, which will in this case be a 3 by 3 vector, let's say 2, 2, 5, okay, and then I ask you find x. Well, you can just put these two into the following matrix and solve it. Okay, and when you get a solution, well, x is in this case just x1, x2, x3. Okay, we want to know what is x1, what is x2, what is x3, right? So if you get the solution here, you will get x1, x2, x3, and it'll actually be the same as the solution for this equation as well. So this is mathematically just a different way of saying the same thing, really. Let's look at a problem here. let's say I give you a matrix A equals 1, 3, 4, -4, 2, -6, -3, -2, -7, and also B equals, let's say, B1, B2, and B3. And I ask, for which B is AX equal B consistent? Well, you should know from the previous theorem that for this to be consistent, this needs to be consistent. Okay, so for this matrix equation to be consistent, this augmented matrix needs to be row equivalent to a matrix which shows you that the system of linear equations represented by this augmented matrix is consistent, which means that it has at least one solution. So here we'll just make the following matrix. And we will row reduce this. And when we row reduce it, we'll end up getting, when we row reduce it and we simplify it, we'll end up getting the following. Okay. So remember that if we have a matrix where one of the rows is 0, 0, 0, and then we have this, and then here we have 5, let's say, then this will give me 0 solutions. Because we can't have 0x1 plus 0x2 plus 0x3 equal 5. This cannot be. This will have mean 0 equals 5, which is nonsense. Okay? So therefore, if I don't want 0 solutions, then I need to have 0, 0, 0, 0 on this side. Okay? So therefore, this here needs to equal 0. Okay? So I can say if B equals B1, B2, B3 such that 0 equals B1 minus B2 over 2 plus B3, then AX equals B is consistent. Okay. And actually, what I can tell you is this equation right here is an equation. Now, you haven't taken a lot of you haven't taken calculus 3, so don't worry if you don't understand this. But I'm just saying this so that I can foster your mathematical, curiosity. This is an equation for a plane. Remember a plane? This is a plane right here, for example. Okay, and it's the equation for the plane through the origin, okay, and it is the span of A1, A2, A3, okay? And remember, this is A1, this is A2, this is A3. So any linear combination of A1, A2, and A3 will end up giving you a vector that points to a point that is on this plane right here, the equation of this plane. And why is that? Well, because we see that for this equation here to be consistent, okay, meaning for B to be a linear combination of the columns of A, then I'll need B1, B2, and B3 to be such that this equation equals 0 right here. Okay, so it turns out that, let's see here. So I have this plane here. The equation for this plane is 0 equals B1 minus B2 over 2 plus B3. Okay, where I have here B1, B2, and B3. All right, so basically the span of the columns of this matrix here, the span of these three vectors here. Okay, so I have the vector A1 equals 1, negative 4, negative 3. A2 equals 3, 2, negative 2. And A3 equals 4, negative 6, negative 7. Okay, the span of these three vectors, meaning the set of all linear combinations of these three vectors, okay, is this plane right here, which means that no matter how I combine these three in a linear combination, for example, 2A1 minus A2 plus 3A3, I will get a vector B, that is on this plane here. You understand? If you don't understand that part, then you don't have to worry about it. You won't be tested on, the geometric interpretation of this question here. But I thought that it was interesting, and so I felt compelled to include it here. Right. Okay. So let me give you the following theorem, which we've already discussed why the results of this theorem hold. Okay, but let's now formalize it in a theorem. So let A be an M by N matrix, meaning it has M rows and N columns. Then the following statements are logically equivalent. Logically equivalent means if one is false, all of them are false. If one is true, all of them are true. Okay? So, for any, this means for any or for all. Okay? For all vectors in m-dimensional space, ax equals b has a solution. This statement is logically equivalent to the following statement. For all vectors in m-dimensional space, B is a linear combination of the columns of A, and this is logically equivalent to the statement the columns of A span the entire m-dimensional Euclidean space. And this is equivalent to saying A has a pivot position in every row. You should know this theorem, okay? And you should know how to use it as well. Be careful though, this theorem does not, it doesn't apply to coefficient matrices. It applies to, it applies to coefficient matrices, not augmented matrices, right? So if I have, for example, the following matrix, where these are any number, and I have 0, well, there's a pivot here, there's a pivot here, there's a pivot here, so there's a pivot in every row. However, this here tells me that there are 0 solutions. Okay? So even though D holds here, this is actually an inconsistent, this system is inconsistent, it does not have a solution. Okay? So these three statements only pertain to the coefficient matrix, not the augmented matrix. Okay? Alright, one last thing and this section will be over. If A is m by n and U and V are n-dimensional matrices, and C is a scalar, which means it's a number, then A can be distributed if we multiply it by the sum of two vectors, these two vectors. Okay, these are just two algebraic properties which you think should be obvious, but I mean, even though they are obvious, they should be pointed out here because we will find that not all properties that work with addition and multiplication for, let's say, numbers not all of those obvious properties work for matrices. So later on you will find that a matrix times another matrix does not always equal the I forget what. Right, so this matrix multiplication is not commutative in this case, right? For numbers it is. 3 times 4 equals 4 times 3, but this isn't always true for matrices. And we haven't learned in general how to multiply matrices yet, but we'll learn that after the midterm. Okay. So your homework for this section section 1.4. And this will be due on November 12th. Okay. And I'll give you instructions on when your midterm will be. And I'll have a review session also where you can ask me questions. And I will go over some homework problems as well. The review session will be sometime next week, but I will announce that a few days before I hold the review session. And if you have any questions about the homework, you're welcome to contact me on Teams. You're welcome to ask me for an appointment on Teams for a video chat where we can do, one-on-one help. Or if you and like 1 or 2 other friends want to get together and make an appointment and you all have questions, please let me know, and I'll be more than happy to make an appointment with you.